Well, hello to everyone. This project is named 3D Shape Classification. It has been done by my colleagues, Sergi Vidal, Juan Pedro Ruiz, Pablo González, and myself, Joan Calafell. Next, please, Pablo.
No, it doesn't work. Okay.
Okay. This will be the outline of the presentation. First of all, I'm going to explain the motivation of the project, then the scope and the timeline we follow to carry out it. Then we will present the data sets we have used for all the training process and validation and test ones. Then we will present the first architecture based on MLPs that we have implemented, which is called PointNet. Then we change to another strategy based on convolutional neural networks for graph neural networks, and we are going also to present these architectures. And finally, we are going to present the test conclusions and the global project ones. Next, Pablo. Well, these are the motivation of the project. Basically, is using a kind of neural networks that can understand point clouds and graph neural networks. And point clouds basically are interested because we can represent 3D geometries with them. And this can be extremely useful for classification purposes of three-dimensional shapes, for instance, or in the case of the autonomous driving, for using 3D images instead of using the traditional two-dimensional. In these kind of images, you have much more information, such, for instance, the depth of the domain where the car is moving. And finally, another useful thing for graph neural networks can be, for instance, for any kind of scientific computation in which special meshes are involved. Next, please. Well, this is the timeline of the project and the steps we have followed to complete it. First of all, what we have done is a research on what kind of data sets we could use for the project. We analyze two types, two different data sets, ShapeNet and ModelNet. Finally, we decide to move on with ModelNet with 10 different categories for classification. In this data set, basically, is a point are 3D objects which are represented through point clouds. Okay. Then we implemented from scratch PointNet, which is an architecture which is basically based on multi-layer perceptrons. We tested the initial data set with this architecture. The main objective of this section, of this part of the project, was basically learning how to implement a full neural network from scratch in Python, and then also learning how to train and well, at the end, finishing it. Just to follow all the network construction process. The problem of PointNet, basically, as I said, is that it's based on multi-layer perceptron. It uses a huge amount of trainable parameters, and that's why we moved them to the graph neural networks. The main advantage of this kind of networks is that they allow to perform convolutional operations, which helps in reducing dramatically the number of learnable parameters of the net. Then we propose the use of two different convolutional layers. One is GCN, which is about from the 2016, and then we use a newer one, which is GAT. We expected it to behave in a better way because basically it also features attention. And then finally, what we did is training and optimizing these nets, because we used an initial baseline, but we followed a logical sequence of tests in order to add different layers and methodologies that could help to make them work better. Okay, next.
Okay, for classifying 3D objects from the dataset, we have used different models. The first one is PointNet, which was the first deep learning framework to directly handle 3D point clouds. On the following slides, I'll explain a little bit about its architecture and the results we have obtained using this model. Next slide, please. Next slide.
Sergi. Sergi.
Es que se me acuerdo la página, no sé por qué. Go ahead, Pablo.
I'm sorry, I was talking on mute. Apologies. I thought I. Well, so yeah, so this is a recall of what we presented already in February. Like as Joan said, we studied two data sets, ShapeNet and ModelNet, and we chose ModelNet for our study, right? So ModelNet is a data set based on meshes. So the files contain vertices and faces. So we wanted to do 3D point cloud analysis. So the first thing we had to do is to create the point cloud from the meshes. Also, we decided that in order to improve the homogeneity of the images and also the density, it was better for our models to scale the images to a homogeneous scale from -1 to +1. Like these, all images have the same sizing, and we thought that the model would learn better the features of each one slice and then be able to classify better the images. And then final step, once we have the point clouds, we had to create the graphs. So for that, we use a KNN algorithm. And you can see in the slide how the process goes from the mesh to the graph. The point cloud is fed then into the PointNet architecture, which is designed for point clouds, and then we fed the graphs into our GNN architectures that we will detail later. In order to address overfitting, and we detected some overfitting in some of the configurations we tested, we also studied several transformations that PyTorch Geometric allows. Here you have some of them. So we explore, we use a couple of them to do that augmentation and then reduce overfitting, as you will see in the next slides when we present our results. So now.
Okay. For classifying the object from the dataset, Pablo, can you mute it?
Sorry?
Pablo, can you mute it?
You can mute yourself. Yeah, there is a echo.
It's difficult because I cannot. Okay, sorry.
I don't see the slides.
Pablo, the presentation has disappeared.
Okay. On the previous one, please. Okay, for classifying 3D objects from the dataset, we have used different models. The first one is PointNet, which was the first deep learning framework to directly handle 3D point clouds. And on the following slides, I'll explain a little bit about its architecture and the results we have obtained with this model. Next slide, please. This is the scheme of the PointNet classification network taken from this paper. This architecture basically takes point cloud as input and outputs class labels for the entire input. This network has three main parts: the input and feeder transform, the shared MLPs, and the max point layer. The input and feeder transform are two transformation networks called TNet that align input points and point feeders to make them invariant to certain transformations, such as rotation or translation of the whole point set. TNet is like a mini point net that predicts the transformation matrix, and it's composed by all the models that come after the feature transformation, such as a shared MLP, max pooling, and two fully connected layers. The shared MLPs are used for learning a spatial and feature encoding for each point and mapping them to a higher dimensional space. And finally, the max pooling layer is used to aggregate information from all the points. This means that the output of max pooling layer compresses the endpoints of the input point cloud to a subset of points, and gives as output a global feature vector that is invariant to the input order. This is done because we want that the same set of points in different order represent the same 3D object. Next slide, please. And the plot on the right shows the training and validation accuracy versus the number of epochs of our model without normalizing the input data. As we can see, the training accuracy is increasing with the number of epochs, getting close to 100%, and the validation accuracy is also increasing, but has many oscillations. On the other hand, the plot on the top right shows the results after normalizing the input data. As you can see, applying an input normalization provides training efficiency and more stability. In this table, we can see the training parameters used for the test according to the PointNet paper, and also shows the maximum accuracy results for training and validation. And now Pablo will explain the other models that we have used on this project, the GNN architecture.
Okay, so I hope you can hear me well. So for 3G classifications, as we said, we explored the graph neuronal networks. We analyzed two types of convolutions, and we define indeed for each one of the convolutions architectures, testing, and we try the different configurations, as you will see. So these are the two convolution networks, convolutional options that we use for graph networks. The first, the graph convolutional networks on the left-hand side, so the GCN1, applies the linear transformation to the feature vectors of the neighbors of the node and additions them. The results are normalized by a constant that depends on the number of edges of degrees of each node. HI is the projection of the node in the output dimension. W is the matrix of weights to learn. As you can see, in this convolution is isotropic, and no H is favored versus any other. So for favoring H's in the graph, we tried as well the graph attention networks, or the GAT convolutions that you see here on the right-hand side. The GAT uses it uses an alpha, so an attention mechanism that is called alpha, and you have is the alpha, the attention score. This attention score is calculated, and we will see some details later through a softmax, so it's already normalized. And here what we are doing is indeed applying different alpha to different edges. So the linear transformation of the features of the neighboring nodes will be multiplied by the different number, and therefore we are able to prioritize some edges against the others. So how this attention mechanism is calculated is following the schema you see here on the left-hand side, right? So what the mechanism of GAT does, it uses an additive attention mechanism. The linear transformation of the node and the linear transformation of one of its neighbors is concatenated, as you can see here below, and multiplied by vector A. This vector A is common for all the graph. A is learned by the network. The result then goes through a leaky ReLU, and then a softmax is used to calculate the alpha from EH. So we are going to calculate, we're going to concatenate the transformation of the features of the node and concatenate it with the transformation of each one of its neighbors transformation, linear transformation, okay? So in the end, we will have a set of E's. We apply a softmax, and then in this way, in the end, the HI you see here on the left-hand side, then will be tuned and by this attention mechanism, this attention score. The good thing of GATS, as implemented in PyTorch geometric, is that you can calculate several attention heads, so you can have several A's. This option allows you indeed to try different configurations in the architecture that we will see later. The result, what the GAT does is for each attention head, you will have an output feature vector, and you have two options of post-processing. What you do with these feature vectors, you can concatenate them. So in the end, you can have a longer feature map, feature vector for the transformation from the convolution, or you can addition it. You can average it. In this case, you will only have a feature vector of the dimension you have defined in the convolution. So the output dimension will be the one that you have defined as output channel. So we have tried the different options. So we have here different heads, different concatenation and averaging of the different output vectors, and we will see the results later today.
Well, now we are going to see the specific architecture of the GCN, which is the first convolutional network we tried. Well, the design process has been more or less like this. So at the beginning, we took a baseline architecture. Basically, was composed of 3 convolutional layers. This value, we took it from the original article of the GCN convolutional operator. And then following these convolutional layers, well, on the top of all those convolutional layers, we added a batch norm and ReLU activations. Then we used a pooling layer for reducing the dimensionality, and finally we added a linear multilayer linear layer in order to perform the classification task. Then in the next slide we will see what has been the logical sequence of tests we have done in order to improve this baseline. Next, Pablo. Well, here in the table, there is a summary of the tests. As you can see in the columns are the different layers and methodologies we tried for each specific test. The first things we tried is improving as much as possible the test and validation accuracies. Of course, during that experiments, the problem we found is that that overfitting appeared. So at the end of the experiments, what we did is trying to reduce as much as possible this overfitting. Well, the first test we performed was to decide whether it was better using an average pooling or a max pooling. As you can see in the table results on the right. The best option by far was using a max pooling, which give much better results than the average one, and that's why we kept this pooling and this max pooling layer for all the rest of the tests. Then another strategy, what we tried was modifying the learning rate. At the beginning, we were using 1⁻³ learning rate value, and we decided to increase it. So as you can see on the right, the results were not very successful. We increased the validation accuracy by 1%, but the problem is that they appear a lot of fluctuations on the training curve, so it became very unstable. And that's why we decided to move to the next experiment that was adding a learning rate scheduler. With this methodology, what we obtained was a much smoother learning rate curves, and the learning process was much more stable than with the previous strategy. Well, once the training process was stable, what we wanted was trying to increase even more the accuracy of the train and validation sets. And that's why we tried to double the capacity of the existing layers. Basically, we multiplied by 2 the feature maps of the input and the output feature maps for all 3 convolutional layers. As you can see, we reached a value of 100% for the train accuracy. But the validation accuracy was not really improved. It was because of the overfitting. And then the next steps we follow was trying to minimize this effect. For that reason, the first approach we took for reducing overfitting was applying dropout. Dropout decreased a lot the training accuracy, but didn't modify too much the validation one. And that's why then we tried also data augmentation. We tried 2 different transforms, flip and rotate. And the one which provided the best or minimized the gap between the training and accuracy losses was random rotate, and that's why, and the one that also provided the best validation accuracy, and that's why we finally decided to keep it for the final strategy. So as a summary, what we have is a max pooling layer with a learning rate scheduler with double capacity, and using the random rotate transform for overfitting minimization. The overall results of this GCN, they really outperform in terms of magnitude the ones of Poinet, but the best or the important point to remark here is that we reach almost the same values by using just a tiny fraction of the trainable parameters we use for Poinet. Poinet had 3.5 million of trainable parameters, and here we used only 12,000. And next slide, please.
Hello, it's Juan Pedro Ruiz. The final step of this project is implementing the graph attention network that is quite similar to the graph convolutional network, but introducing attention heads at the end of each layer. We test this architecture, modifying the number of attention heads, and we're starting from 4. By default, we have a concatenation of the heads, but we test also the network doing an average. We also use regularization techniques as dropout or data augmentation to reduce overfitting. Please, Pablo, next slide. Okay. In this table, we show the sequence of experiments that we follow to improve the performance of the network. As a starting point, we use 4 attention heads in each layer, and we compare the performance of the network with 2 initial learning rates in the scheduler. As we can see, the best performance is given by the 0.001 initial learning rate. The next step is to check if increasing the size of the network to 8 heads, attention heads, it's capable of learning more complex features. At the same time, we check if reducing size to 2 heads is able to generalize better the data. As we can see, the best result is given by the 8 attention heads network. So the following tests have been done on it. Another way to try to reduce the size of the network to improve its generalization has been by averaging the heads, but as we can see in the table, these tests do not improve the performance of the network.
So 1 minute.
Sorry?
1 minute, please. 1 minute.
Okay. Finally, we apply different regularization techniques to reduce overfitting, such as dropout and data augmentation using the random rotate and random flip transforms. We have obtained the best results with the random flip. In the graph, we compare the 4 attention heads baseline with this final network, where we can see that the operation followed have improved the performance of the network. Please, next slide. And finally, we made a comparison of the 3 architectures that we have been used in this project. The first thing that we can see is that despite the fact that the PointNet has the best test accuracy, we have achieved that graph attention network has a similar performance by reducing the number of parameters 20 times, but due to attention heads, the training time is higher. Analyzing the precision and recall by class, we can see that the same pattern is followed in the 3 networks. For example, table and desk have low precision and recall scores. The same goes for dresser and nightstand. This may be due to the fact that at the beginning of the models are scaled, which can lead to confusion from the point of view of the network. Please, Pablo.
You should finish, please.
Okay.
Go to the conclusions, Pablo.
Sorry?
Next
Go to the conclusions. And, okay.
Yes.
And finally, the conclusion of our project are the following ones. We have been able to implement a deep learning network from a research paper to solve the task of classification 3D object from point clouds. And we have learned to use graph neural networks for 3D classification. And we make a wide variety of experiments following a scientific approach to increase models' performance. And as a final conclusion of our experiments, we could say that we have created a GN architecture that performs similar to PointNet with 20 times less learnable parameters. And that's it. Do you have any questions?